Hello, hello. Welcome, welcome. Hello, everybody. Please feel free to say hi in the chat if you are here. Hopefully you can see my screen okay and everything is doing what it should be. But yes, hello, welcome. Welcome to our Sunday sessions. This is A-level chemistry on intermolecular forces. So this is mainly for year 12 students, but if you're a year 13 student, this is also going to be a very good revision for you. We're going to be looking at the different types of intermolecular forces, some really good key phrases for exam technique to do with them. And we're going to be focusing on, well, hopefully been having a go at doing some exam questions and that sort of thing. So hello, welcome if you're here. Please feel free to say hi in the chat. Hello, Arsene. Apologies if I've said your name wrong. Hi, K-Drama Addict, welcome back. I recognise your name from previous sessions. Double hi, lovely, good. Yes, welcome if this is the first time you've been to one of our sessions, please feel free to go and have a look at our YouTube class and go back through the classes, YouTube, what's it called? Our, YouTube section. We've got loads of videos up there, and hopefully all of the slides and stuff that go with all the videos should up there as well. So, it'd be great if you're an A-level student doing a bit of revision, it's a great idea for you to go back and have a look over some of our previous web classes. There's loads of revision that you can do there. Also, feel free to check out our website as well. There's also some free content on there as well. Hi, Jane. Lovely to have you here. Hi, Steve. I think I recognise your name from previous as well. We'll get started in just a second. We're just going to give everyone another 30 seconds or so to appear, if they're going to appear, and then we'll get started. So this is one of our A-level chemistry web classes, our Sunday sessions, bit of revision for us all. I know that, leading up to, lots of us might be leading up to exams, maybe, could be your actual exams, could be predicted grade exams. So hi, Labour. Apologies if I've said your name wrong, and Star Girl, 777 Star Girl, nice to have you here as well. This should be just under an hour, so hopefully we'll be finished by 7 p.m. UK time. These web classes are suitable for all exam boards. We are focusing mainly on the main 3 in the UK, which is AQA, OCR and Edexcel. But a lot of the content at A-level chemistry is very, very similar across the board. Especially stuff like this, which is the kind of the basic core content. So let's get started then. So a little bit about me. I've been teaching at Snap Revise for years now. I can't actually remember when I started, 2019 I think it was. I'm the lead GCSE, not GCSE, I'm just the lead chemistry teacher here at Snap Revise. I've got a PGC in chemistry education or science, but specialising in chemistry from Oxford. And I've been teaching science, including A-level chemistry, for over 7 years now, so long time. I do love it. I think it's great. And I think A-level chemistry is one of the hardest A-levels, without a doubt, but also incredibly interesting and incredibly useful and just a fascinating subject. So I love it. Okay, so our objectives for this session, so it'll be about an hour, just under. Hopefully we will look at understanding instantaneous to induced dipole bonds and their physical properties, what the impact they have on substances. We're going to look at understanding permanent dipole-dipole bonds and their physical properties. And we're going to look at hydrogen bonds and their physical properties. So those are the 3 main types of intermolecular force. We'll discuss some names and phrases and stuff as we go along. We're not going to look at physical properties of hydrocarbons. We do actually do a little bit of that. I think it was our last chemistry session on YouTube. We did a little bit of that in there, so feel free to go back and watch that on our YouTube channel. That's the word I was looking for earlier. And then we're also not going to look at intermolecular forces in water versus ice. That does come up in some of the specs very specifically, but we don't cover that specifically on our web classes. So if you are an AQA student, these are the spec points that we're hoping to cover in our sessions today. So have a quick read through and double check that you're happy with what's expected of you. OCR students, if you're an OCR student, these are the spec points that you would want to be covering, that we are going to be covering, for you. So have a quick look through and see what it is that's expected from you. This is where ice comes in specifically for you. So we're not going to be covering that. And edXL, if you're an edXL student, again, have a read through, double check that you're happy with that. If you're doing other exam boards, then obviously feel free to have your specification up in front of you, because you can use that to check what we're doing. Specifications are incredibly useful if you're a student. If you're an AS, as in year 12 student, they're incredibly useful for looking at how content links together, for making sure you're solid on the secure on the content that you need to have previously. If you're doing revision and you come across exam questions, they're very useful to check if you need to be able to know it already, or if it's a year 13 content question. So they're incredibly useful. They're also useful if you're year 13, because they're a checklist of everything you should now already know or be able to do. But interpreting specifications can be quite tricky, so it is worth going through that with your teacher or a tutor or somebody, just to make sure that you're happy with what's expected of you. Okay, so what do we already know? Hopefully this is a revision class for everybody, so you should be able to tell me, type it in the chat. Feel free to kind of add to each other's answers. If somebody gives a good answer, you can say, yeah, that looks great. Or if you want to change a keyword or add in some details, then do that. But what is the definition of electronegativity? And this is something we need to know word for word, basically, because there are key phrases that they're looking for in the exam. So what would we use? What phrase would we use, or phrasing would we use to describe electronegativity, do we think? In an exam, what would you say? Hello, hold on. Just to answer your question while we're waiting. Is there a specific schedule for the chemistry sessions, and do the lessons repeat? There isn't a specific schedule. I just teach whatever I'm told to teach. We try not to repeat the sessions too much, but there will be a repeat year on year, obviously, because the content repeats year on year. So hopefully that helps, but there should be a list of all the chemistry sessions that we've previously done. I think it's intertwined with the list for maths, physics and biology as well, so you might have to do a little bit of kind of scrolling through, but it should all be on our channel under previous uploads, live uploads, in that section a bit. And is this similar to the Cambridge syllabus? Yes, there is a lot of very similar content. Like I said at the beginning, all of the core content, I call it basic content. It's not basic in terms of complexity, but in terms of core knowledge, it's all very similar across the exam boards. There's very little difference. Okay, this looks good. So it's really nice. Yeah. Fantastic. So loads of people have given us some good answers there. Eden, that's good. Stargirl, that was good. Jane, looking good. Kosar as well. Apologies if I'm pronouncing names wrong. I'm doing my best. And Zenu, I will have go. Zenunoli. That looks great. So there's some key phrases that we've got in there. It's the ability or power, you can say. The ability or power of an atom, very nice, to attract and it's always a pair of electrons, because whenever we talk about electronegativity, although we take it out of context, and that can get confusing for students, when we talk about electronegativity in terms of Pauling's electronegativity, when we can give it a number, we're talking about its ability to attract a pair of electrons in a covalent bond. So well done if you said that. To attract a pair of electrons in a covalent bond. And it's slightly unnecessary because we said attract, which means towards anyway, but they're looking for something in your phrasing that says towards itself, so attracting towards itself. Now, like I say, you can get that by saying attract, but if you use another word that's not the word, not attract, if you said pull or move or something like that, you would need to say towards the atom. Towards, whoops, with an S. Okay, lovely. Apologies for my handwriting. The pen setup I'm using at the moment is not ideal because technology laptops don't like me for some reason. So apologies, my handwriting might be a little bit scrappy at the moment, but I will do my best. Let me know if you actually can't read anything though. Okay, so how do we, I mean, you guys can only type, but have a go. How do we show a partial negative charge in a structure on a compound? What do we, if we're trying to do a partial negative charge, what do we say? And also partial positive, again, what do we use? Anybody got any ideas? Yeah, good, well done, delta minus. The delta symbol, the D, which is lowercase delta. And so for negative, it's delta negative. And for partial positive charge, it's delta positive. Very good. Yeah, well done. Lovely. Easy peasy. We also should know how to represent a dipole, and this could be in a simple molecule such as HCl, which has got a dipole across the bond, where our fluorine is significantly more electronegative than the hydrogen. So the chlorine atom is attracting the electrons in the bond. So we're going to get a delta negative on the chlorine side. That's where most of the electrons are at the moment, or where there's more electronegative charge. And then there's a more electropositive charge across the hydrogen. Or it could be across a molecule, or within a molecule, even I should say, not across, I should say within a molecule, such as a molecule like that. So our carbon is going to be delta positive and our iodine is going to be delta negative here. Again, iodine's more electronegative, so we're going to get a dipole, a split of charge. Dipole, di meaning two, poles, as in positive and negative, poles, as in polar opposites, things that are opposite to one another. So a dipole is where you've got two charges. If you're showing a dipole, you have to have two charges. Cool. Okay, good. Hopefully that's all super easy. So let's have a look at our intermolecular forces. I'm going to try and focus on some of the key words and phrases that are useful for us when doing these kind of, when doing exam questions to do with these, intermolecular forces, because that's often where we can lose marks. So I will try to be as specific as possible. So in non-polar bonds, electrons are in constant motion. This means that at times non-permanent dipoles can instantaneously form. There should be an S there, really, shouldn't there? Non-permanent dipoles, oh dear, that S looks a bit weird, instantaneously form. Usually, these kind of forces are called what? Instantaneous induced dipoles are referred to as what? What's a name for this kind of interaction? Does anybody know? London forces, good. Now, there is actually a difference. You can do induced dipole, that's good, Christopher, yeah, lovely as well. Well done, Steve, for saying London forces. You may also hear, and I'm going to put it in brackets, you may also see van der Waals. Now, this is actually mainly from old spec questions. So if you come across a question where they've asked about van der Waals forces, it's likely to have come from an old spec question, because we've moved on to using the term London forces, or being very specific in calling them instantaneous induced dipole bonds. Yeah, so van der Waals is like old phrasing. You can use it, and most of the time they will allow it because it has been in use constantly for years. But if we're being very on spec, we should be using the terms London forces, or being very specific with them being instantaneous to induced dipole bonds. So when we've got normal bonds, I'm going to non-polar, I should be specific. When we've got non-polar bonds, or bonds that are normally non-polar, for example, those within methane, if we look at the electron movement or the electron placement within methane, in a carbon-hydrogen bond, normally electrons exist very centrally between the two atoms. However, every now and again, they might be slightly towards one side, perhaps. free movement. Although we show electrons being in bonds, there is free movement. They can exist within the bonding orbitals wherever they want within the bonding orbitals, which means they are moving around. They are constantly moving. And at any one point, they could be over, both of the electrons could be both over one side of the molecule, or conversely, they could both be over the other side of the molecule. And that can happen randomly. This is a random movement. It's a good phrase to use. The random movement of electrons can cause one side of a molecule to be slightly delta positive and the other side to be slightly delta negative. It can cause an instantaneous dipole. So this is, these two can be instantaneous, just check my spelling, instantaneous dipoles. Again, hopefully none of this is new. So if I just show kind of the general spread, so fairly average. On some cases, maybe we've got a bigger negative charge over one side. In some cases, perhaps there's a bigger negative charge over the other side. That way, therefore, we've got dipoles appearing, instantaneous dipoles appearing. So in this case, we've got our delta negative that side, delta positive that side. Here we've got delta positive that side, delta negative that side. Very good. Okay. Oh, we'll come to questions in 2 seconds once I've gone through this, but I have registered we've got questions. So we then, if you have an instantaneous dipole forming, in that instant, there is a dipole. And that instantaneous dipole can induce a dipole in a neighboring molecule. Let's just show that occurring here. The induction, inducing something, is causing it in another molecule. So if you've got two molecules that are sat next to one another, and we have, let's say, an instantaneous dipole formed in our one molecule, then the positive side of the dipole can attract the negative electrons in the neighboring molecule, inducing a dipole in the neighboring molecule. Here we get an induction. It can also obviously happen in reverse, however. Let me just get my pen back onto blue. It can also happen in reverse. What if we have our dipole the other way round? Then we can get the negative electrons, or sorry, the negative dipole on one molecule repelling the electrons in a neighboring molecule, pushing the electrons away to the other side of the neighboring molecule. And again, that's inducing a dipole in the neighboring molecule. Two ways, attraction and repulsion. But in both cases, we end up with two dipoles next to one another. And I don't know why I did those in blue, so let's just go over them in red, so they're a bit clearer. In both cases, we have had an instantaneous dipole that's appeared and induced a dipole in the neighboring molecule. So here we get nearby electrons. I'm just being lazy and using E- for electrons. In an exam, you should write the whole word. I'm just being lazy now. Nearby electrons repel or attract. Sorry, are repelled. Let's do that again. Nearby electrons are repelled or attracted. Attracted by the dipole in the neighboring molecule. And then we end up with two molecules with dipoles next to one another that can attract one another, can be attracted. Oops. So if we've got a dipole in the first molecule, so our first molecule was instantaneous, a dipole formed instantaneously, there was just random movement of electrons, it induced a dipole in the neighboring molecule, and then we have a positive and a negative next to each other, a delta positive and a delta negative, and for a fraction of a second, we can get an attraction between those two delta positives and delta negatives. The same thing can happen in reverse, depending on how our movement of electrons has occurred. Let's say we have it in reverse. We have our delta positive this side, delta negative that side. It's induced a dipole in the neighboring molecule. And again, we therefore have a delta positive next to a delta negative, and they can attract one another. We get the attraction, and it's instantaneous. And then the electrons will move on and move somewhere else, and we lose the dipole, and then we lose the attraction. So these are very weak, very, very weak intermolecular forces, but you still get the attraction. So here we have our instantaneous to induced dipole forces. And that attraction that we need to overcome, this is our London force. Okay, let's address questions. So how will we know which element is more delta positive? If you're talking about an instantaneous dipole, then either could be. We are only likely to want to describe instantaneous induced dipoles in molecules where you don't already have a polar bond, so where there isn't one element that is much more electronegative than another. So thinking about electronegativity, picture the periodic table. Fluorine is the most electronegative element, and in general, it's not an exact science, but in general, as you move away from fluorine, so away from fluorine across the period and away from fluorine down the period, everything gets less electronegative. In general, that's a very general trend. It's not very specific, but very general trend. So as you move away from fluorine, everything gets less electronegative. So if you're thinking about, are we likely to have a polar bond? If you've got an element that's very near to fluorine in the periodic table and an element that's very far away from fluorine in the periodic table and they're bonded, such as hydrogen and chlorine, then you will get a polar bond. So in terms of how will we know which element is more delta positive, it could be either. If your bond is not already polar, then either could be delta positive because it's just random movement of electrons. Sometimes they're over here, sometimes they're over there. It wouldn't matter. If you were asked to draw the interaction, if you were asked to draw this intermolecular force in an exam, then they would accept either being delta positive or delta negative. Hopefully that answers your question. Polar bonds, does the shape of the molecule change whether or not there is polarity? Oh, that's a good question. Does the shape of the molecule change whether or not there is polarity? No, I don't believe it does. I can't think of any reason why it would. I mean, definitely not at A level. We do not consider it to change at A level. But as we know, everything we learn throughout a lot of science is a model, is a simplified model of what actually happens. So when we talk about shapes of molecules, we have simplified them ever so slightly. So saying that every molecule is that has 4 bonds is tetrahedral, or not every, but most molecules that have 4 bonds are tetrahedral, is also already a little bit of an oversimplification. So there are other things that determine shape, and polarity would be impacted by the elements and the atoms and the groups of atoms. So that would also technically have an effect. At A level, no, it doesn't. Technically, yes, but there are also lots of other things that influence shape as well that we don't touch on at A level. So hopefully that answers your question, Christopher. Is this only for non-polar compounds? No, technically, any molecule will have London forces occurring within it because electrons move randomly all over the place. So, but if you've got a polar bond already, then you're also already going to have another type of intermolecular force, which we'll come on to look at in a second. Lone pairs of electrons do affect the shape. Yes, they do. And we do that at A level. We look at that at A level, definitely. Why is London force the weakest? Very good question. It is the weakest because the initial formation of the dipole is instantaneous and random, and it's just due to the movement of electrons, and the electrons are moving randomly, so, and fast and all over the place. So you will only get an instantaneous dipole forming, which will very briefly influence the neighboring molecule. You get a very brief attraction between the opposite dipoles in neighboring molecules, and then they've moved on and it's gone. So the reason it's weakest is because they're so instantaneous and they disappear very quickly. So they're such small interactions, it's very easy to overcome them. Hence, they're the weakest. Hopefully, I've answered all the questions. I think I have. Okay, good questions, very good questions. We'll move on to the next type now, and hopefully we can have a look through those. So next type of intermolecular force is our permanent dipole to permanent dipole interaction. Very similar to the one we've just looked at, but we just skip the first step. So here we've already, oh, sorry, my pen's being weird. Hold on, sorry, I can't get my pen to appear. Oh, there we go. Oh no, apologies, it's just done a silly. Let me just get it to stop doing that. Try that again. It sorted itself out. Good. Oh, and now I can't see your chat. There we go. What was I saying? I've distracted myself now. Oh. Oh no, my pen's disconnected. No, it hasn't. Okay, good. Let's try that again. So, permanent dipoles to permanent dipoles. So these occur, oh, that's what I was saying. So because we've already got permanent dipoles in the molecule, we skip the first step of the random movement of electrons. So we've already got permanent dipoles. So again, if we use the same example we used before, if it'll let me. Oh, it's playing up. I don't know why. Sorry, team. My screen is being really odd and I've got no idea why. Oops. Is that? No, it's still not working. Sorry, team, bear with me. I'm just trying to sort this out because my screen has decided. Let's see if I can get it. Like this. No, still won't work. Let me try one more thing. No, I think my my second screen is picking up. Oh, it was working fine. Sorry, team, just bear with me. Technology is never fun when it goes wrong. What is it doing? Why is it doing that? Sorry, guys, you're being super patient with me. I'm just trying to see if I can get my second screen to work. Otherwise, I can't write. But it's decided it's not happy for some reason. Just randomly stopped working. Okay. Ooh, sort of, even though that CL's gone funny, but we'll cope with it. Okay. And everybody see my screen again. Just did a little reset thing and it seems to have liked it. Can you let me know that you can see my screen and hear everything okay? Yeah? Awesome. Brilliant. Okay. Fingers crossed it stays okay. That's an irritation, isn't it? So we'll try and carry on and see, and hopefully everything will stay happy. Okay, so permanent dipoles, permanent dipoles, permanent dipole to permanent dipole bonds. In molecules with permanent dipoles, opposite partial charges attract each other. So when we've got molecules with bonds where one atom is more electronegative, much more electronegative, sorry, than another atom, there will be a permanent dipole present. As in, although the electrons do move around all over the place, they will, on average, spend more time around one atom than they will around another. Here, we know that that atom would be chlorine, so the electrons will spend more time around chlorine than they will around hydrogen in both molecules, because chlorine is more electronegative. It has a higher ability to attract a pair of electrons in a covalent bond. So the electrons in the bond will be spending, on average, more time around the chlorine at all times. Therefore, we have a permanent dipole already present. If we have a permanent dipole present, then there will constantly be an attraction between molecules and the neighboring molecule, between the delta positive in one molecule and the delta negative in another, or vice versa, the delta negative in one molecule and the delta positive in another. And this we call a permanent dipole bond. We are only interested, or we only discuss bonds, interactions as being permanent dipoles to permanent dipoles if we can't then call them a hydrogen bond, which we're going to go on to look at in a second. So this is our attraction, and this is our permanent, I can never remember how to spell it, permanent to permanent, dipole. The attraction between the delta positive on one molecule and the delta negative on another, or delta negative on one molecule and the delta positive on the other, whichever way around. This is slightly more, slightly stronger intermolecular force, because the dipoles are there permanently. So In previous, it was instantaneous dipole to induced dipole because it happened instantaneously and then it stopped happening again. So they happened, didn't happen, happened, didn't happen, happened, didn't happen, happened, didn't happen, etc. Here, the dipoles are permanent. We permanently have one side of the molecule that's more delta positive or delta negative than the other. So there will always be the ability to have the attraction to another molecule that has got a permanent delta positive, permanent delta positive, permanent delta negative. Is there a bond angle to the PD? Oh, that's a very good question. Very, very good question. Not that I have seen in mark schemes. I don't see them get too worried, but in the same way with the hydrogen bonds, that's a very, very good question. I would try to get a 180-degree angle between the bonds. So that might be more important when you're doing something like showing, like we did earlier, with the interaction between a CH3, no, an iodide iodomethane molecule and a neighboring iodomethane molecule, in that you'll want to get almost as kind of a straight line between the molecules. This is my delta negative, so that's my delta positive. So again, that's my delta positive, that's my delta negative. So the interaction would want to be as straight as possible. If you started drawing it off to the side, it's going to look a bit funny. But having said that, I don't think I've seen any mark schemes where they penalize it, whereas they definitely do in the hydrogen bond. So that's a very good, good thing to note. Okay, let's move on to hydrogen bonds then. Super, super useful, super exciting. And one of the reasons we think, as scientists, we think we have life on Earth, because hydrogen bonding occurs, and it means that water has these awesome properties, which means life can be based around water. So hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular force. Hydrogen bonding occurs between a delta positive hydrogen. It has to be a delta positive hydrogen, so the hydrogen has to be connected to a very electronegative element so that it has a delta positive on it, and three of our very most electronegative elements: chlorine, nitrogen, and oxygen. Sorry, fluorine, nitrogen, and oxygen. I said chlorine, I meant fluorine. Fluorine, nitrogen, and oxygen. They are very strong compared to other intermolecular forces because we have got this interaction. So, very good point from Christopher earlier is we do need to be thinking about our diagrams and what's important in the diagrams. So specifically, a 180-degree angle is important. And I'll show you what I mean by that. We'll do it with water because water is such an important molecule. So, ooh, that's supposed to be an oxygen. There we go. If we have an oxygen molecule, we should know the shape of an oxygen molecule. What shape is oxygen? What shape is water? Apologies. What shape is a water molecule? What shape do we say that a water molecule has? Very good. Lovely. Bent or non-linear. You can say non-linear as well, but bent. Because it has two lone pairs. Now it's based on a tetrahedral structure, with the two lone pairs also taking up two of the tetrahedral structure shapes. And then the bond angle has been squished, so it's no longer 109.5, it's actually 105. Yeah, 105. I had to do a quick bit of maths then. And the important thing is that our hydrogen is going to be delta positive because it's attached to a very electronegative element, oxygen. So our oxygen is delta negative, our hydrogen is delta positive, both hydrogens are delta positive. And we can get an interaction then between the delta positive hydrogen in that water molecule and the lone pair on a neighboring element. Specifically, the lone pair. That's why, I'll come to your question in a second. That's why we have Oh no, it's 104.5, isn't it? I can't do maths. I thought I could do maths. I can't do maths. It's 104.5. Sorry, I can't do maths. That's why hydrogen bonds can only occur between hydrogen and oxygen, a nitrogen and a fluorine, because we must have a lone pair of electrons available to interact. So let's just do my dipoles. So sorry, yeah, just to clarify that the shape of water is 109.5 minus 2.5 is 107, minus 2.5 is 104.5. I can't do maths. 104.5 degrees is bond angle. To be honest, though, they do accept a range because, as we literally just touched on a couple of slides earlier, this is a simplification of the model. So actually, the bond angles do vary ever so slightly, but we need a way to discuss it. We need a way to learn about it and to think about other chemical principles, and therefore this is our simplification of the model. Oh, hello. That's supposed to be delta positive, delta positive. So we get an interaction between the delta positive hydrogen, and it's delta positive because it's connected to an electronegative element, and the lone pair on a neighboring electronegative element, either oxygen, fluorine, or nitrogen. And that's our hydrogen bond. I'm going to be lazy and just call it a H bond. In your exams, you should call it a hydrogen bond. So that is our H bond. It should be covalently bonded. The hydrogen should be covalently bonded to an electronegative element. And the 180 degrees needs to be between the oxygen-hydrogen bond and the hydrogen-oxygen bond. There needs to be 180 degrees like that across the molecules. This is because our lone pair is I shouldn't have done my bonds so long there, actually. Let me just get rid of that a little bit. Should have just gone as far as there. And that's because of the position of the lone pair. If we start drawing our bond like that, that's a weird shape because the lone pair isn't going to be pointing out in that direction. Lone pairs are pointing in a specific direction. Think back to your shapes compared to the bonds in oxygen and hydrogen, and we try to show that where possible. So that would be incorrect. I'm getting rid of that orange one at the top because that would be very incorrect. As well as having, showing the interaction there between the hydrogen on our main water molecule, I'm going to call it the main one, and the lone pair on the oxygen on a neighboring one, we can also show the interaction between the lone pair on the oxygen of our main water molecule and a hydrogen in a neighboring molecule. Again, this is where we need to get our 180 degrees. You need to point out from the lone pair across the hydrogen-oxygen bond, and then you can add in your other hydrogen-oxygen bond where appropriate. But again, we need to always need to label your delta positives and delta negatives. Must always make sure you label your lone pairs where they are appropriate, because you will get marked on that. And again, we need to have 180 degrees across the hydrogen bond between the oxygen and the hydrogen-oxygen bond as well. Must be 180 degrees. Oops, I haven't done my delta negative oxygen either. There we go. If the other hydrogens that aren't involved in hydrogen bonding, you can obviously still label them as delta positive because they are delta positive, but they're not involved in the bonding. So for completeness, I like to include them, but actually, because they're not involved in the bonding, your examiner isn't going to be looking for them. They are only going to be looking for the delta positives and delta negatives and lone pairs that are involved in the bond that you're showing. So those are my H bonds there. Okay, why are hydrogen bonds strong? Because hydrogens are very small, easily polarized. The bonds with hydrogen are easily polarized. So it forms a partial positive charge when bonded with very electronegative elements V electronegative elements. Just trying to make up time now. Negative elements. Specifically, and we do need to be very specifically, oxygen, nitrogen, sorry, we do need to be very specific, oxygen, nitrogen, fluorine. If you've got a hydrogen bonded with something else, it's not a hydrogen bond. You cannot form hydrogen bonds. The way that they interact, the way that the atoms interact is not correct enough, would not cause a hydrogen bond to occur. So if you have a hydrogen bonded to a chlorine, because of the difference in size between hydrogen and chlorine, you don't get the same effect, therefore you don't get hydrogen bonding. Similarly with hydrogen and bromine, similarly with hydrogen and sulfur. There are other effects and other interesting things that happen. So you get polar bonds and you get permanent dipole-dipole attractions, but you don't get hydrogen bonding. So hydrogen is small and easily polarized, so forms a partial positive charge when bonded with very electronegative elements, or I should put bonded with the lone pair on, apologies, we're bonded, that's supposed to be a star, oh my goodness, my handwriting is appalling. It's supposed to be a star. When bonded with the lone pair on very electronegative elements, oxygen, nitrogen, and fluorine. Okay, anybody got any questions about that? I'm just going to add that in at the top there as well. I've put the lone pair, obviously some of them have got more than one lone pair, but it's just one of the lone pairs that they're interacting with. If anyone's not happy, drop me a message, but also, can you have a think, how confident are you feeling about those 3 different types of intermolecular force? What are we thinking about those? Are you feeling confident? That was fairly straightforward. I'm quite happy with that. 2 or a face means that was okay. I'm probably going to need to check up on some of my keywords maybe, and maybe do a couple of exam questions. Or 3 or is, oh my gosh, that was horrible. What criteria can we use to know how big the difference needs to be in electronegativity for polar bonds to be present? That's a good question. There's only one exam board that requires a difference, and I can't for the life of me remember which one it is. I think it's EdXL, but don't quote me on that. And there needs to be an electronegativity difference of, I believe it's 0.4 between the Pauling numbers. Pauli, I keep saying Pauling, I think Pauli numbers, but I'm not, again, don't quote me on that. You're basically, if you're looking for there to be a polar bond, look for anything with a anything bonded to a halogen is definitely going to be polar. Oh, actually, not definitely, that's a bad phrase. There are, okay, let me say it like this. There are some bonds that come up over and over again in A-level chemistry that we need to know are polar, such as chlorine hydrogen bonding, carbon halogen bonds, hydrogen sulfur bonds, oxygen hydrogen bonds, hydrogen halogen bonds, those ones. And if you think about it, apart from carbon, which is obviously ever so slightly closer, anything bonded to anything to an element on the left-hand side of the table, such as hydrogen, is going to be a very polar bond. And we know that anything, for example, group 1 metals bonded with halogens, non-metals, we actually get ionic bonding. So it's so electronegative, the bond is broken. We've donated a pair of electrons. Apologies, Sylvester, I can't help you there. We've only got it on YouTube at the moment. We got told, oh, okay, to remember that. So as in anything bonded. Wait, what, Christopher, you're going to need to explain that to me. What, as in hydrogen bonding with any of those? is a polar bond. And Labour, is it enough for us to just know those for AQA? I would say yes, but most of the time in an exam, they will give you information to help you work out whether or not something is or isn't going to be polar. But those ones I just listed are definitely polar. So anything else, you're going to be looking for information to work out whether or not it is or isn't going to be polar. And Christopher, I would trust your teachers, absolutely, definitely trust your teachers, but personally, I would not say that chlorine and bromine do hydrogen bonding, because they're just the difference in polarity between hydrogen and chlorine and hydrogen and bromine is not big enough for there to be as big enough dipole to form you'd get permanent dipole bonding, but not hydrogen bonding. So yeah. Oh, right. Okay, cool. In which case, yes. Lovely. That's great. Yeah, those would form polar bonds. Right, I need to whiz on because I've realized we're a little bit behind. So because we are a little bit behind, I'm just going to skip this exam question. Apologies. I do want to try to get through as much of the content as possible, and I know that it's my fault, technology's fault that we've missed it. So apologies for that, but we're going to skip past that exam question and just have a look at properties. So the physical properties of some small simple molecules such as carbon dioxide, water and methane are dependent on the intermolecular forces between the molecules. This trend this pattern will help us to determine how strong the attraction between molecules are. And as we've just spoken about, we have the weakest type of intermolecular force, our London forces, or instantaneous to induced dipole bonds. Then we have a slightly stronger interaction which can occur between some molecules, which is our permanent dipoles, attractions. And then we have hydrogen bonding. Hydrogen bonding is the strongest attraction between molecules. It's not a bond. I know we call it hydrogen bonding, but it's really just a force, an attraction between molecules that we can describe and talk about. So if we're trying to work out how strong an attraction between molecules are, and therefore think about their boiling point and melting point, we need to think about how many instantaneous dipoles you've got, instantaneous to induced dipoles you've got, sorry, how many London forces, how many permanent dipoles you've got, and how many hydrogen bonds. So, oh, hello. That's gone funny. Let's try that again. I'll do it in blue as well. So, the number of instantaneous to induced dipole attractions or forces that are present, and also the size of them. So in another web class, we talk about our halogen molecules. As they get bigger, you have more electrons. That means you can have a bigger dipole, a bigger difference in charge within a molecule, and therefore you can get a greater attraction to a neighboring molecule. So our number of instantaneous dipole forces / the size of them. We can also look at the number of permanent to permanent dipoles forces. Oops, put the dash in the wrong place. The number of permanent dipole to permanent dipole forces / attractions again. And the number of hydrogen bonds. Again, I'm going to be lazy just because we're running out of time by putting H bonds. As we go across this scale, what happens to the boiling point and melting point? So as we go here from left to right, as we go As we increase the number of instantaneous to induced dipole attractions, as we increase the number of permanent dipoles we have, and in a substance where we have more or at least have hydrogen bonding, what's going to happen to the boiling point of our substances? Oh, that was supposed to be a straight arrow. Didn't go so well. Never mind. Yeah, good. So boiling point and melting point increase because why? Why do the boiling points and melting points increase as we increase the number of attractions we've got? What can we do to explain it? Anyone know? Yeah, exactly right. Well done, both of you. So more energy is required to overcome the forces. Very nice phrasing. Well done, Stargo. Well done, Christopher. Well done, Sylvester. Because more energy, again, I'm going to be lazy. E for energy is required to overcome the forces. And you could be very specific in an exam question. You can talk about more energy is required to overcome the hydrogen bonds or whatever it is. If you have been asked about something specific, then you can give more. You can be specific. Now, this is why I like to say overcome, not breaking bonds. I want to talk about them being more energy needed to overcome the forces. And yeah, also, Christopher, a good note, if we're talking about between, for example, chlorine molecules versus between bromine molecules, you might want to talk about the stronger or greater. I like to use the words greater. It kind of is a catch-all, which is quite nice, but greater intermolecular forces as well. Yeah, good. Okay. The other thing that we can think about very briefly before we run out of time is solubility. So the solubility of small simple molecules depends on the polarity of the solvent and the solute. Just check you're happy with the difference between those words, what they mean. So polar molecules, what do they dissolve well in? Sorry. Polar molecules dissolve well in what type of solvent? And can you give me an example? E.g. water, love it, yeah. Polar molecules dissolve well in polar solvents. So this is all exam boards we're covering here. Polar solvents, polar and polar. Think about, well, if you want to try and understand it, it's to do with their interactions. If you've got a magnet and you're trying to interact it with something that's not magnetic, they're not going to interact. If you have a magnet and you want to try and interact with something that's magnetic, you will get an interaction. It's the same thing here. If you've got a polar molecule and you want to try and dissolve it, you need to dissolve it in a polar solvent because you want the molecules in the solute and the solvent to interact. So they both need to be of the same type. They both need to be polar in order for them to interact. Then the polar bonds, the positives and negatives can interact, break up the particles, and you get solubility. Same in reverse, non-polar molecules dissolve well in non-polar solvents. For the same reason, again, or kind of converse reason. If you've got two non-polar molecules, they are going to be able to interact with one another because there's no random polarity in there kind of messing things up. They're both non-polar, so they're going to be able to interact nicely, and therefore your solute is going to dissolve in your solvent easily. An example would be something like, what's that called? Tetrachloromethane, CCl4. Super quickly, what kind of intermolecular forces are involved in the solvation of polar molecules? So when we've got polar molecules dissolving in polar solvents, what are the intermolecular forces that are likely to be present or can be present? Anybody know? Hydrogen bonds, good. Not all the time, obviously, because it does depend on what substance we've got, but we could have hydrogen bonds involved. What else could we have? Good. Permanent dipole, permanent dipole. Very nice. So permanent to permanent interactions or forces, etc. And instantaneous induced as well. Yeah, lovely. Our London forces. Very good. Just to reiterate, in exams, you can use these phrases interchangeably. London forces versus van der Waals versus instantaneous to induced dipoles. You can use those terms interchangeably. I would stick with London forces or instantaneous to induced dipoles, just to be specific, because van der Waals is actually an umbrella term for other things as well. So although it used to be taught as van der Waals, we've kind of clarified it, and now we call it London forces, or specifically instantaneous to induced dipoles. What about with non-polar molecules? What kind of intermolecular forces are involved in the solvation of non-polar molecules? Only London forces, only our instantaneous to induced dipole forces, because that's the only ones that can be present between the molecules. Lovely. Okay. So again, sorry, we've totally run out of time to have a go at the exam question, but feel free to have a go at it, and hopefully we've covered enough of the theory that you should be confident in answering it using the theory that we've already covered in this session. So we're going to have to skip past that. So we've looked at instantaneous to induced dipole bonds, i.e. London forces, and how they occur. We've looked at permanent dipole bonds and how they occur, and we've looked at hydrogen bonds and how they occur. We've looked briefly at solubility and some of the properties, i.e. melting points, and how they're affected. Does anyone have any questions about anything that I can answer now before we disappear? Do we need to know anything about cohesion and adhesion? Oh, if you are in AQA, OCR, and EdXL, I don't believe so, no. We look a little bit at, come on, brain. Heterogeneous catalysis in year 13, and the action of heterogeneous catalysis, which talks a little bit about other interactions, but I don't believe you need to know about cohesion and adhesion for the three main exam boards anyway. Anybody else have any other questions? Cool. Apologies again for technological hitches. It seems to have sorted itself out, so don't know what happened there, but thank you so much for being patient with us. Again, don't feel free to go back through our what's it called? I had the name earlier. Was it YouTube channel? That's it. Please feel free to go back through the YouTube channel, watch all of our previous videos. We've got lots of lives up there as well, and lots of videos that you can just watch that were pre-recorded. We've also got lots of our notes, so you can use our slides and notes to make notes and revision notes, etc. Oh, OCRB, okay, that would be why. So this is OCRA content. OCRB is a little bit annoying, isn't it? So yeah, bad luck. Hydrogen bonds in ice. So just super quick, we weren't going to cover it, but I will just say really briefly, hydrogen bonds in ice, the reason they're so important and so exciting is because the crystal structure of ice, when water hydrogen bonds with water, when you slow the temperature down, when you lower the temperature enough that it becomes solid, i.e. ice, the hydrogen bonds, the way you can get a very strong hydrogen bond actually is where the molecules are slightly further apart, and then they fit into this beautiful crystal structure when they're slightly further apart from one another. And that can only happen when the temperature is low enough that their movement is limited, and therefore it's a solid structure. And that's why ice is less dense than water. And there's only a very, very, very few substances in which that is the case. Most cases, when you increase the energy, you increase the movement, and then you increase the volume. So most things will be, get it right, more dense as a solid than they are as a liquid, than they are as a gas. But water acts in the opposite, in that it is, make sure I get it right, less dense as ice, and then it becomes more dense as liquid, and then goes less dense again as a gas. So that's the weird one. It's because of the hydrogen bonds, they sit ever so slightly further apart. The molecules sit ever so slightly further apart to get the perfect hydrogen bond between water molecules. And that's why. That's the weirdness. That's a very brief summary of the weirdness. Okay. Thank you very much, guys. Apologies, we overran ever so slightly. I'm going to disappear now and let you guys get on with your days. Have a lovely evening. Don't forget to check the schedule, find out when our next sessions are. And we've also got biology, physics and maths happening as well. So enjoy. I will see you all hopefully soon on another web class. Thank you all very much. Bye. Thank you.